Hello, my name is Robert Smith and I'm with New River Community College, and today we are looking at the dissolution of salts so in this particular case we're being asked to calculate the pH and the percent hydrolysis of a 0.51 molar solution of sodium acetate. Now, for all salts, sodium acetate being one of them, they will completely dissolve in solution or dissolute. And that means that this sodium ion will break off of the acetate ion. So you'll be left with Na plus and CH3COO minus. So when you think about these kinds of things, what we're being asked really is how is this going to affect the acidity or basicity of the solution of the water that we're dissolving the salt into. And the thing to recognize is that the sodium ion is going to be a spectator ion, so it will not participate. It will not hydrolyze at all. And hydrolyze is just reactions with water. So what we're more interested in is what this acetate ion is doing. And to do that, we're going to start by setting up an ice table. And in fact, we're going to use two ice tables in this. The first one is just kind of to illustrate how this whole process is occurring, but the second one is more essential. The first one you could rationalize in your mind if you'd rather, but in essence, what we're doing is we have to write a reaction where the salt dissolutes. So to do that, first let me erase all this. So to do that, what we're going to do is we're going to write out the reaction where sodium acetate dissolves in water to yield the acetate ion and the sodium ion. Okay, that's about done. Okay, so we start off with sodium sodium acetate, so CH3COONA, and that's going to completely dissolve into Na plus and CH3COO minus. Okay, and we're going to do our ice table like we would normally do. And in it, we know that we start off with 0.51 molar. And we're going to just put molar up here so we know what unit we're working in. So 0.51 molar of sodium acetate. And at the outset, before we're dissolving anything, we're assuming there's no sodium ions and no acetate ions. And then the change will be, because we know this is completely dissolving or dissoluting, as is indicated by the one-way arrow, we know that we're subtracting 0.51 molar. And whenever we subtract on the reactant side, we have to add to the product side the same amount weighted to the coefficient. Now the coefficient on each of these terms is 1, so that makes it rather easy. So we got 0.51 and plus 0.51. Okay, so then at equilibrium, we have no sodium acetate and we have 0.51 molar of sodium and 0.51 molar of acetate ion. So that kind of tells us that all that was for was just so that we can recognize that while we have 0.51 molar sodium acetate. Once it dissolves, we will also have 0.51 molar of acetate ion. So this was just kind of a setup so that you kind of see it very clearly what's happening. But you could just as easily say, well, I know that when sodium acetate breaks apart, that I should have, for every one sodium acetate that broke apart, I should have one acetate and one ion and one sodium ion. So automatically that would tell me that I should have 0.51 molar of acetate ions. You could do that as well. I just wanted to illustrate it very explicitly. So now we know sodium is not going to hydrolyze for a number of reasons. First of all, it basically resulting in the fact that it's an ineffective acid. Sodium simply just does not react with water the way that acetate will. Acetate will react with water to produce either an acid or a base, and we're going to figure that out together right now. So if you take the, that was our first ice table, so now we're moving on to our second ice table. So we need a new reaction, which is just the acetate ion plus water. And that's going to be in equilibrium. And what's going to happen is you can tell from the minus sign that acetate is a base. Or it has basic qualities. So what's going to happen is it's going to deprotonate, which means remove a hydrogen from our water. In fact, it's not really hydrogen, it's actually a proton that it's removing, H+. So what'll happen is it'll go into equilibrium with acetic acid, which is where it gets that extra H. And plus, I'm going to put down here because I'm running out of room, OH minus. So hydroxide. So what we learned from this is that acetate ions in solution will produce, will increase the pH of the solution, make it more basic, because you'll end up with free hydroxide ions in solution. Okay. So now we need to put down all the information. And in this time, we're going to start off with our 0.51 molar for our acetate ion. So 0, I guess I should put the ice, 0.51. Water, we're not really concerned with anything that goes on in water because we're considering water to be so abundant that it will not have a change in concentration relative to the other species. So that's fairly standard, especially in Gen Chem. You normally don't have to worry about water concentrations changing. And then at the outset, we also have 0 acetic acid and 0 hydroxide. Now our change is some unknown. We know that the acetate ion will decrease by some value, but we're not sure what that value is. So we put an X. And similarly, we know that for every acetic acid, there should be a corresponding, or for every acetate ion, there should be a corresponding acetic acid. So we know that's going to go up by some value. And because there's one water per every acetate ion in this equation, we also know that our hydroxide is going up by the same unit. So for our equilibrium equations, we have 0.51 minus X. And for acetic acid, we have X. And for hydroxide, we have X. So next, what we would need to do is take the values that were given. We'd have to look up what is the, because we're dealing with hydroxide, we want to look up the Kb, the basic dissociation constant for acetate ion. And when you do, you find that that Kb is equal to 5.6. Sorry, that's a terrible 5, but times 10 to the minus 10. So we have 5.6 times 10 to the minus 10, and we can set that equal to what we know to be products over reactants. So that would be the concentration of acetic acid, which in this case is X, times the concentration of hydroxide, which is in this case is X. So that gives us X squared at the top, over our reactants, which we're only considering the acetate ion. So we can put a 0.51 minus X. And when you compare this, the thing to recognize is what the concentration here is versus once you've applied this term to X, such a very small value, our kV, that we can approximate this as X squared over 0.51. And that makes our calculations a lot easier. Once you solve for X by multiplying both sides by 0.51 and then taking the square root of both sides, you will find that we can rewrite our X as equaling 1.69 times 10 to the minus 5. And recall that that would be molar because the unit of X in each of these cases and each of these terms is going to be molar. And this is also equal to the concentration of our acetic acid, but also more importantly, our hydroxide ions. So from there, we can look at using that to find out what our pH is. And to do that, we first find our pOH by taking the negative log of the concentration of hydroxide, which will be 1.69 times 10 to the minus 5. And that'll give us a pOH of 4.77. And pH, we know, is simply 14 minus pOH, which will give us a value of pH of 9.23. So you saw, just by doing this calculation, we can determine that the water went from a pH of 7 to a pH of 9.23 simply by adding acetate ions to it. The next part of the question was asking for the percent hydrolysis. And in order to do that, all you do is you take what the concentration of your hydroxide is over your initial concentration of the acetate ion. So you're basically looking at what is the percent effect on the overall solution, the water, and acetate ion. So percent hydrolysis would simply be let's call it 1.7 times 10 to the minus 5. 1.69, 1.7. It's going to give us roughly the same number. And then 0.51 as molar as our initial concentration. And if we multiply by 100%, then we end up getting 0.0033%. So that's our percent hydrolysis. It's very small. Typically, you'll only have very small percent hydrolysis in these kinds of cases. So, quick review. We were asked to calculate the pH and the percent hydrolysis of a solution of sodium acetate with a given molarity of concentration of 0.51 molar. And what we did first was we did an ice table, although you could just simply recognize that as a salt, it's going to completely dissolve and you're going to have the same concentration of your acetate ion as you did of your sodium acetate. This is true because there's a 1-to-1 relation between them. If there was a 2-to-1 relation, then you'd have to adjust for that. It's kind of like the Van Hoff factor, although that's more for vapor pressure lowering and things of that nature. And then we did an ice table that actually involved a variable and unknown, and that unknown also signified the concentration of our hydroxide. We retrieved our basic dissociation constant for sodium for acetate ion from our textbook, and we then calculated what X would be using an approximation method. And once we've calculated what X was, we knew what that also equaled the concentration of the hydroxide ion. We calculated pOH, and then used that to calculate pH, and that gave us a pH of 9.23. And we also calculated the percent hydrolysis from the concentration of hydroxide by relating it to the original concentration of the acetate ion. And that gave us a percent of 0.0033%. And that's all there is for today. Thank you so much.